Welcome to join the seminars today. Just to make sure, like for people attending the room, you can hear us clearly. If you don't, feel free to send in the chat. So let me first introduce our speaker today, Dr. Shijun Liang from MSU, Michigan State University. So he has been working with Psy and also got a PhD this year from the biomedical engineering at MSU. So his research has been pretty broadly into the machine learning relevant approach for the medical image reconstruction and also the other computational imaging. And particularly, recently we have some potential collaborations on the diffusion model relevant approach. He has also been working on for the DIP, the deep image prior for enhanced the robustness for the image reconstruction as well. So we're very happy to invite Shijun to give us this in-person seminar talk today. And let's welcome our speaker and feel free to take your time, Shijun.
Oh, thank you for attending the talk today. I want to give my thesis talk about advancing imaging reconstruction and restoration through robust, supervised, and generative model. And thank you for the introduction from Professor. So I would go through from the outline of a talk from the introduction and motivation about the MI reconstruction from two aspects. And then I will go through the work of self-guided image prior to go through the first topic. And the remaining two will be related to the another topic for some diffuse imaging robust imaging reconstruction, like the SMUG, which is the smooth unrolling, and the adversarial purification for robust reconstruction. And then I will go through the conclusion and talk about some future plan. Inverse problem is the pretty wide application for the different domain, especially like MI reconstruction. It can like provide the innovative and some functional information for the radiologist to analyze some information from the patient, but the data collection and acquisition is time consuming. In order to get the full case-based images, like the corresponding ground truth case-based, to gain the ground truth imaging is like you need to collect all of the images. So people try to like only sample the low frequency and some random high frequency information to accelerating the processes. Then you can get the matrix case base. But if you're directly doing the inverse IFFT reconstruction, then you got the pretty blurred images that will like not providing sufficient information for the radiologist. So people try to using the compressed sensing reconstruction, but the performance is like still like slightly poor in that case. And there are still a lot of application like imaging denoising to removing the Gaussian noise in the images, or the imaging in painting to recover some missing information, or like the center of the mixing pixel, or even like images moving to like smooth out some unwanted detail of the images to give some more preferred information for the customer and so on. But this is all related to the pretty common problem for the least square problem, like the imaging reconstruction. So for example, when you have the different for operator, you can like you can define different problem for the data validity term. Like for example, for the MI, the A operator will composing of the Fourier transform operator, the sensitivity map when you're doing the multi-coil MI reconstruction, and some sampling mask to sampling the necessary information in the case space. Or for imaging in painting is like some mask operator, or some Gaussian blurring is the Gaussian blurring kernel, and so on. So in order to solve this problem, if you directly do the inverse operation, then you can get unlimited solution. So people normally can using the regularizer to helping you to solve this problem to get the more desirable solution that you want, like adding the TV regularization of regularization and even like the L1 regularization to gain the sparse solution in order to get the more matching information and provide the more meaningful information in that scenario. And you can like constrain the regularization to get the more easy information in that case, and can determine the smoothness of the some information into the images. But for the imaging reconstruction for medical imaging, especially for MI, you need to like face two kind of the challenging, like the data scarcity. For example, especially due to the patient privacy, it's like pretty hard to think at much data set in like the natural imaging data set. And some kind of the noise also will be like pretty challenging for the MI reconstruction. Especially like MI data collection is pretty time consuming, and it will also further reduce the data availability. And how to handle of the out of the distribution test data can, for example, like the patient lesion in the knees or some white tissue in the brain slide can also kind of the out of distribution test data set that can like dramatic drop of the test imaging reconstruction performance. And so like the traditional method, like the deep learning and transform learning can like handle this kind of limited data scenario, but the performance will be like dramatic less effective compared to the deep learning approach. Or why the deep learning performance can provide a pretty strong and superior performance. But in this scenario, like the MI reconstruction, maybe you will lack of sufficient data set. So how to improve the robustness of those kind of MI reconstruction method can be important. And this is the two main challenging I'm working on. So I will go through for the data scarcity with the following project first. And before that, I will go through some recent work like the compressed sensing that explore the sparsity in the transform domain in order to reconstruct the sparse solution to get the desirable solution in that case, or like the deep learning that to learn on the limit data set with using the patches. So you will optimize with the learn dictionary and the sparse coding by doing the bilinear optimization, or you can like providing the more efficient transform learning based method that you want to like learning the specify signal in the transform domain. In that case, you can solve the sparse coding in the pretty closed-form solution that can like accelerating the transform learning study. Or like some recent advance like the deep neural network that can like provide pretty comfortable solution like to solve the MI reconstruction for undersample case space when you have the pretty large amount of the training data set. But for example, when you have no training data set, how you can solve this problem? So people try to study the unsupervised learning called the deep inspired DIP method. So in this problem, you are mainly solving the problem one. So you have only the neural network and the input is the random noise that you fitting into the neural network. And you only have the Y measurement is your target images. In this case, you will only like minimizing your neural network in order to give you some feasible solution. The main reason that it can be working for the DIP is the over-parameterized parameters of the neural network. So in that case, you can think the neural network as some kind of low pass filter that can like learning the low frequency information from the target images. And then by increasing the iteration, you can like learning some like high frequency information on the images. Then the neural network can like learn from the measurement of the single images as the implicit regularization of the reconstruction problem in this case. But the drawback of the deep inquiry is like since you are learning on only one single images and to reconstruct the single output, then it's like pretty easy to overfitting in this case. And normally the DIP will be like optimized using the ADAM. And in order to avoid the overfitting phenomenon for the dignifier, people normally using the early stopping. So when you reach the peak performance, people will just like try to stop at this criteria at the peak point. But how you like manually controlling of the peak performance is like pretty time consuming. For example, for the following MI reconstruction performance, as you can see, when you have the zero field reconstruction, fitting some random Gaussian noise fitting into neural network, you can see the performance will increase dramatically for the original 1000 iteration, but it will like decrease after that. This is the overfitting issue in this case, as the performance will be decreasing as the iteration increasing in this scenario. For example, you can reach the peak performance like iteration like 240, but after like 5,000 iteration, you can see the imaging will full of the Gaussian noise or some random artifact that will occupy the whole images in this case, compared to the ground truth images. And it's even like slightly worse than the zero field reconstruction that you're directly using the inverse forward transform to get the images. So they have many work have been introduced to solve this problem. Like for example, like changing the network architecture from the common CNN to the deep decoder. A deep decoder will only composing of the decoder part of the network that by skipping the encoder in order to avoid the overparameterization phenomenon in the neural network. In that case, you can like avoid the early stopping more efficiently. Or if you can like adding the regularization like in order to controlling the degree of freedom of the neural network. So in that case, you can like also controlling when you can stop for the to get the more easy early stopping to get the peak performance, or even you can like changing the optimization algorithm by injecting the Gaussian noise into the network weight. In this case, you will not like sampling from only one single point. You can like sample from the posterior distribution, or even like changing the network parameter, like by controlling the Lipschitz constant of the convolution layer, because you can the Lipschitz constant will be controlling of the spectrum long of the parameter. So by tuning the specific constant, the frequency information will more focusing on the low frequency of the images in that case. But how to understand this phenomenon for the dignifier is like we'll call this overfitting issue will be called a spectrum bias. It's because of the neural network will learn the low frequency information, image content more quickly and more accurately than the high frequency content. So people will try to using the neural tangent kernel to analyze this phenomenon better. It's a mathematical tool to like analyze the training dynamic of the neural network in the infinity-wise setting. People normally focusing on the spectrum bias phenomenon that will happening on the imaging denoising, but we're also doing some experiment on the MI reconstruction setting. So we would like have three different kind of the frequency mask, the low frequency mask, middle frequency mask, and the high frequency mask on the case-based images. And we will test on the sampling mask on the full acceleration case. As you can see, even for the MI reconstruction, you can see the low frequency information will decrease more faster than the middle and high frequency information in this case. So to understand this phenomenon, we also doing some analysis for the MI reconstruction. by using some by using the neural intention kernel. Especially when you're optimizing the DIP object on the equation 1, which is the common least square problem, you can get the corresponding change of the network output in each iteration of the network when you do the network updating, where the J is the Jacobian matrix in this case. By getting the gradient of the equation 1, you can get the, by using the chain rule, you can get the more explicit gradient update in each iteration. And then finally, you can get the equation 5 to get the network update for the each iteration. And then by substituting this result back to the equation 4, you can get the more each iteration output network update for the recursion cases. In this case, the J times J transpose is called the neural tangent kernel, and we will be denoting this W as the W in the subsequent section. So based on some gradient update, we got some theorem to understanding this phenomenon. It would pretty depending on the condition of the NTK kernel W. So when the NTK kernel is non-singular, then the error reconstruction will be happening on the null space of the A operator. So the most of the information, if you of your input is happening on the null space operator, then you can never recover some kind of the missing high frequency information of the MI reconstruction. And if your NTK kernel is singular, then the reconstruction will be pretty depending on the range space of the NTK kernel, which is pretty incoherent. If only the null space and of the A operator is incoherence of the range space of the W, the projection of them is equal to 0, then you can reconstruct the exactly ground truth images that you in that case. That means some information is you can get from the neural network. That's why you can get the exact reconstruction. And in order, after we get some understanding for the neural network, we think the information of the input is pretty important for the image prior that can help us to accelerating the reconstruction performance and somehow avoid the overfitting phenomenon in the deep image prior reconstruction. That's why based on some recent work, they just are using some reference images, which is pretty identical to the imaging that you've been to reconstruct. For example, you have the list images, you can try to find some similar neighborhood that can share some similar information. That in that case, that when you use that reference images to fit into neural network rather than using the total random Gaussian noise, that can accelerating the imaging reconstruction. But in this case, even it can helping you to improving the performance, but it's still some you need to some data that can give you some pretty good initialization. So we want to also avoiding those reference images, because if the extreme scenario you have no data set, so how you can avoid is we want to introduce the self-guided EIP, so you don't need to have any reference imaging anymore. Basically, we will have the noise, besides with the data consistency that we introduced, the EIP format, we also want to add in the denoiser recognition that will iteratively perturb the input with the random noise. And then we want to doing the randomized smoothing, which is some recent advance that can make the denoiser more robust for some image classification. And we will slightly introduce that randomized smoothing in the later section. Yes, UNet is the same. We try to avoiding the deep decoder network architecture because the deep decoder you mostly is the imaging that can have some latent information, but we want to also the input have some like more spatial information that can help up to like do some information to refine in that case based on the paper called reference DIP in this case. So that's why we want to introduce the denoiser regularization in this case that can like perturb some images to refine some more detail. And by doing the bilateral optimization, then we can get some input update and then fitting the input to the next network up training in this case to do the network update the next iteration. As we can see for the flow chart is like we would create when you have the initial input, you would like create multiple Gaussian noise to the images to perturb the input. And then when you do the randomized smoothing, you can get the expectation output to fit into neural network. And then you would do some iterating for the network input update and the network update in each iteration. And then we were doing some data correction to get the final output. And we also doing some ablation study to understand whether the regularization is like important in this case. As we can see, when you drop the regularization in this cases, then the performance will drop dramatically in this case. And when you fitting like adding to 1 to 2 range, it will reach the peak performance. So it means the denoiser regularization will help the method work better in these cases. So in order to understand the performance compared to like some DIP scrim or the compressed sensing reconstruction, and even with the supervised new CNN denoiser and some zero-shoot self-supervised learning and some plug and play method, we found out that our method can like better than the supervised unit when you have only like 4,000 to 5,000 images data. We think when the supervised neural network have like more data set, the performance will be better than us. So we just like we want to claim our method can be like better than some supervised method when the data is like slightly less sufficient in this case. And some more visualization, as we can see, especially for our method self-guided DIP compared to the some supervised neural net, our method can like creating the high frequency information more sharpened compared to the self-supervised case. The self-supervised neural net will be like showing some over smoothing for the center area in this case. And our method will be much better than the reference guided DIP and vanilla DIP. Noise imaging for the.
Sorry.
We also doing some like lesion need data set to do some out of distribution study, but actually hard to tell how is out of distribution for the unsupervised method. But we also want to like see when you have the mass shifting or some random Gaussian noise added or Poisson noise added, our method can still like reconstruct the imaging slightly well.
I'm still regarding for the have investigate a little on that, or how to think that will the trend or optimization on
We have some ablation study. We found that when you have the slightly high amount of the noise injecting to the input, that can like help you to get a better performance. I think it's also slightly related to the randomized smoothing, because when you have the highest noise injecting, then you have the higher radius of the L2 bond. So some slightly error that was fitting into the L2 bond, then you can like recover the data is still like inside of the distribution in that case.
I think would be some of the relevant words actually.
Of the MER.
Yes, the without part is really different. Yeah, the different scale. That will be very interesting to think about the way it's space. Yeah.
Yes, I think it's like pretty related, but I think the main difference is the network architecture for NERF is like using the MLP, like a pretty simple network. And I think our method will be more suitable for the UNet in this case. But maybe some network architecture like the transformer is still worth for investigation.
Yes.
First, like the spectral bias slightly lower than actual unit. Either here has stronger bias. But still, in the control basic, the especially the prior depends on the like the forward basis. And so if the lower frequency basis it gives like similar. Also it tells low noise.
Yeah, I guess the definitely was to invest. And we also want to do some robust DIP, so some network architecture changing, and even some more advanced network architectures also like to study. So we're also doing some spectrum bias comparison when we're adding the regularization. We also can see that we can have the low frequency information study faster than without any regularization, and also compare with the high frequency information, we can also achieve the learning slightly faster than the linear DIP method and the reference guided DIP. But yeah, it's still like some trade-off, our self-guided DIP will be have the slightly longer reconstruction time. So we also have some method called the ASIC DIP that we have been improving that drawback, but we try to we can talk about that later. But for the remaining talk, I was more focusing on the robust MI reconstruction, like how you handling the out of distribution dataset more easily. And we want to introduce some model-based deep learning reconstruction method called MODL. It's a pretty famous supervised method for the MI reconstruction. In this method, it will alternate between updating the Z, which is the denoiser output, and we want to also solving the least square problem to make sure the output is consistent with the measurement. So it will iterating this, updating this to denoiser output and the output from the least square update. And it will like this method is like unrolling for few iteration, and the network is still like trained end to end with a supervised training in this case. But what happen if you have some like worst case perturbation that will injecting to the MI reconstruction also? This is the slightly more famous topic for the imaging classification, but slightly less was introduced for the MI reconstruction. The reason why we want to also study for this worst case perturbation is like if the MI reconstruction can handle the worst case perturbation, then the reconstructor can be more robust for the another kind of the when some noise that we will introduce. But for the PGT for the adversarial perturbation is called kind of PGT attack. The main goal is to like maximum the differences between the network output when you're adding the small kind of the perturbation compared with the ground truth images. That's why you can like when even the noise that was pretty scaled by the pretty small amount of the noise, but when you're injecting this noise into the input, then it will creating the pretty worst case perturbation into the images. For example, this is the corresponding imaging when you fitting like only 25 sampling acceleration input fitting in the MODL model, it can like reconstruct the high frequency information pretty good. But when you add in some kind of the worst case perturbation input, then it was like directly make loss of the high frequency information in this case. Or even you like changing the sampling acceleration from only 25% to 50%, but the input is like out of the distribution. It also can like make the network output quite different from without any perturbation. Or even like when you have the change of the iteration in the unrolling base, it also can like sacrifice some information in this case. So we want to like handle this kind of some full quality imaging that was perturbed by some random noise or the worst case perturbation, or even you change of the sampling mask factor and the change of the iteration on the unrolling space stream. So one of the defense method is called randomized spoofing that we also introduced for the self-guided DIP. The idea is pretty simple. You just like creating a multiple noisy copy of the input, and then you would do the averaging in the final output in this case. After you do, for example, for MODL, you go through the denoiser and the data consistency block, and after several iterations, then you do the averaging, then you can get the robust output in this case. But we don't think this randomized spoofing, when you directly fitting to the unrolling method, is the most suitable way to solve the problem. So we want to introduce like the unrolling spoofing called SMUG. And we want to like solve the following four main questions, like how to integrate the randomized spoofing to the unrolling algorithm, such as MODL or some unrolling method like Ethernet or ADMM-net and so on, and how to learn the neural network in the presence of the randomized spoofing operation. And can we like prove the robustness of this randomized of the SMUG in the presence of the data perturbation? And can we like further improving the robust operation in the SMUG can be enhancing the imaging quality or sharpness? So for the solution of the first question is like, rather than have the final randomized spoofing, we want to randomized spoofing in the intermediate unrolling denoiser case. So we will do the randomized spoofing in the each iteration between the denoiser update and the data consistency block update. And in this case, we think by have more unrolling step of the randomized spoofing, it can like improving the robustness. But that will be introduced for the serum that we want to understand this why the have more unrolling randomized spoofing will be better. But how to train this kind of network, we will composing of pre-training and fine-tuning. So we will have the pre-trained denoiser that we can have some robust array initialization of the denoising target images. So we have the denoiser that will only adding some random Gauss noise to the target images to fit into the neural network and to do the pre-training. And in the fine-tuning step, we also introduce the unroll stability loss. The unroll stability loss will kind of adding some kind of encoder regularization in this case. By integrating the supervised MODL and fine-tuning, we can get the final output of the SMUG in this case. And the reason why we think adding more randomized spoofing in iteration is like, when you assume the bounding output for the initial images, the Hermitian Y, and when we compare with the SMUG output, when you're adding some random noise, the error bound will be constrained by the constant C, which is close related to the number of the step of the unrolling step. As we can see, when the number of the step of the unrolling increasing, the error bound will decreasing in this case. This is because with the sufficient smoothing, the error of the smart output will never get worse than the input side, and it can provide the more stability and accuracy in the trade-off of the how much noise that you're adding into the input to do the randomized smoothing. This is that can give us the optimal range of the sigma noise in this case. And to further improving the randomized unrolling randomized smoothing, we want to also introduce the weighted smoothing. So we were using the weighted encoder to train and to give us the most optimal range of how much portion of each imaging to do the weighted averaging. And we think in this case, it can providing us some more sharpened images. However, in this case, we cannot provide some like theoretical result to prove why adding the weighted smoothing is better, but we just providing some empirical result to compare with some different kind of the noise scenario. As we can see, in the trade-off when you're adding the randomized smoothing, the clean accuracy will slightly worse than the vanilla MODL. But when you're adding some random Gaussian noise and even the worst case project PGD attack, our method like the weighting smog and the smog will provide a better performance in the trade-off when you're adding some kind of defense method in this case. And for some MI reconstruction with the need, we also can observe some more sharper feature with the weighted smog and smog. And our smart method can more robust to different kind variety of perturbation. As you increasing the perturbation strength, our method can get a slightly more stable result than the vanilla MODL and some more defense method like the adversarial training and or even for the diffusion model like the score MRI, our method can more stable and provide more better performance than those kind of the method. And even you changing the acceleration factor from 4 to 8, we also can provide some more stable result. And we also compare our method with some unrolling method, like the deep equilibrium method and the original SMART and weight MODL. We can also observe the similar phenomenon.
For the change of acceleration factors, that is for the same sampling trajectory.
Yeah.
So have you tried with the different trajectory?
Yeah, we studied that on the adversarial purification paper.
Yes.
I think it seems like if you're using the diffusion model, it's more robust, and I think most of the researchers also absorb this phenomenon.
Yes.
In that case. Yeah, but even the smart can enhancing the robustness of the unrolling method, but it's still not pretty straightforward to extend to any model. It only fitting for the unrolling method that can integrating this mechanism. So we want to introduce the diffusion purification as some more further extension. The idea is pretty simple. We just want to using the diffusion purification as the purifier rather than the denoiser in this case. And then when we using so this will be using the purification as using the pre-trained diffusion model. And then we will using the output from the diffusion model to fit into the neural network, different neural network to do the further improving for the denoising result. And we think that in this framework we can enhancing the deep learning based MI reconstructor to against different kind of the perturbation and another instability. Diffusion model is famous and that you're composing of the 4 SDE to gradually increasing the noise to the data, and then you would slightly decreasing some random noise in each iteration by using the score model to predict what kind of noise that you're adding in each iteration. And the denoising score matching can help us to like using the neural network to predict the data distribution better in this by using the diffusion model. The reason why we want to using the diffusion purification is based on one of the ICML paper that was introduced, like using a diffusion purifier to purify the adversarial images to get some purified images. When you using the purified images, it can like classify the imagings as the panda rather than gibbon in this case. So we want to using the similar technique to integrate into the MRI reconstruction. In that case, we only using the score MRI, which is like slightly slow right now. So people try to using the DDIM to accelerating the sampling step to get the better performance. We also try to use the DDS, and we also observe a similar phenomenon. So we think our method can like integrating well with different kind of the purifier of the diffusion model. But the score MI is like pretty helpful at the time. It's like you want to using the predictor step to get the score information and using the corrector step to by adding the posterior of information to help you to get the correct measurement rather than using the diffusion model to generate some random images at that case. So our method will be like simple, is like composing of diffusion stage rather than have the random Gaussian noise images. We will directly injecting the input with some adversarial attack noise that by gradually adding the noise to the specific time step, and then we will do the gradually removing the noise using the diffusion model. So it's like slightly different for the standard diffusion model because in our case, we don't need to like reach to the max iteration. We just want to reach some settle point of the images because we want to like, we don't want to remove whole of the information if you directly keep increasing the Gaussian noise into the images. Then in that case, it's slightly hard to bring it back to get some helpful information by using diffusion model. And the intuition why diffusion purification will be helpful, will be working is when you keep adding the Gaussian noise to the data distribution that was have the perturbation and also with the data distribution with the clean data set. If you keep adding noise to the both data distribution, it will reach the same convergence like to the total Gaussian, as the Gaussian noise in adding to the both distribution, they will converging to the same cases, or even for the marginal case and the conditional case. That's why we think our method can be like suitable for different kind of the noisy distribution in this case. And then when you have the purified perturbed example, we can using the some kind of these simple denoiser to do the fine tuning. And we also, so following is a flow chart that we can observe the phenomenon more easily. So we have the perturbed images, we will go through the diffusion stage and purification stage. Then when you get some purified output, you can using the fine-tuning denoiser to get the more sharpened images. If you don't doing the diffusion purifier, then you will get the pretty worse images, which is like lack of most of the high frequency information. So that's why, and we also have the more experiment to compare with the different random noise or some PGD attack, and even the some kind of worst case auto attack our method can be better than the vanilla MODL. And even for the clean accuracy case, our method can still better than the vanilla MODL and the randomized smoothing, or even SMART that we observe that will have the significant trade-off between the robust accuracy and the clean accuracy. But in the diffusion purification, you don't face this kind of the challenging in this case. So in conclusion, we provide a lot of the data scarcity solution for the, like for example, like the self-guided DIP that we introduced that can like using an unsupervised neural network to train the single imaging to handle different kind of the to improving the reconstruction performance even you have no data set. And the robust improvement that we like introduce the SMART and diffusion purification to handle this kind of the issue. So in the overall contribution, we advance the deep learning capacity in the predict constraint setting and improving the reliability of the model-based solution. And for the ongoing and future work, we also want to efficient enhancement for the diffusion model. Like we mentioned, the diffusion model is like pretty slow for the score MI that can like take 1,000 steps of the reverse sampling to get the final output. But we also introduced like SIPCON that can like integrating the triple consistency into the diffusion model. One of the 4 consistency is based on resampling paper that we also. But we also have some inspiration for the self-guided DIP that we want to have the input update. That's why that can make this SIPCON method can be efficient reconstruction. For the future work, we want to like, for example, like integrating diffusion model with the image prior to improving the data adaptation, like some DDoX, like to, they were also integrating the DIP to have some to train the diffusion denoiser. I also saw the patch diffusion model, the OOD also have the similar method. And we also want to like extend the patch diffusion or deep image prior to the 3D reconstruction images, especially with some pretty noisy and limited data, and to also understanding some theorem for the series of the diffusion model and DIP. Thank you.
Okay, great. Thank you so much. And is there any questions from audience? And also the people on the chat, feel free to raise your questions by unmuting yourself or put in the chat. So I want to ask a quick question about this new summation. So what exactly do you mean by the triple consistency? So is the prior, is the visual, so what's the other?
And the input update as the forward. Yes, like the self-guided DIP. We want to have the in each iteration, we want to make sure the input update is consistent with the level update to make sure that's the acting some kind of the denoiser regularization. That's why we call the input consistent.
So you're also updates like the
image measurement with input.
That also on
Yeah, on the archive and hopefully get some score maybe 2
Yeah.
weeks later.
Everyone else like 2 weeks. Okay, cool. Any other questions? Yes.
So about the adversarial persuasion, what exactly are the scenarios you are modeling the real world like acquisition?
Yeah, like we mentioned, if the model can robust enough to the worst case scenario, then it can like handle like the sampling shifting, and when you have the lesion injecting on what's inside on the case space, on the measurement, it will also can like recover those kind of the scenario better in
So
that case.
feel like the sampling structure is not like correctly measured.
Yes.
But then there will be phase error in the application. Right? Is the network to those phase errors?
That's why we also want to introduce the diffusion purification that can like give some initial better result that can like reconstruct some feature better in that case. Yeah, we want to study that for the deep interpreter also, but we also have some region transformer on the EEG signal, and we also have some study on that. We want to using the region transformer that, no, the transformer to understand the EEG signal. We don't apply the region transformer or the deep interpreter.
Tried by some.
Yeah.
Sure. There's no strong spice in example.
Yeah, that can be especially helpful for the unsupervised method that we think.
And so for the sitcom paper, I highly suggest you check out the recent clear 25 paper, which is called the gradient projected like diffusion solver, so that project the data consistent term on the manifold of the noisy sample. And I would suggest you compare with that paper if any future work. So for purification, so I'm wondering, do you have a principal method of using the forward time step?
Yeah, we have the study to determine the forward time step, like we call the PST time step.
Yes, so however, as my past knowledge, so the reconstruction performance with the forward time step is a very nonlinear procedure, so there exists a sweet spot of time ranges.
Yes,
So after, before the time range, the image looks quite close to the input image, and after that time range, the image looks really different.
yes, that's why we have the sweep time spot by using the MMD matrix to fine tune the settle point in that case.
Okay, yeah, so I suggest you check out our sync frequency, so the variable will be flexible out there. First.
Yeah, that would be helpful. Maybe I want to discuss with you later to get some information.
The paper else.
Yeah,
So we also under the submission message, so we'll see. Okay, cool. Any other questions from the audience? Yeah, looks like no question from the chat. I think we're in a good timing here to end. Thank you so much, everyone, for coming here in person, and look forward to hear more from the research student. Thanks for giving such a nice time.
Thank you so much for the invitation.